Okay, here we are in 3.3. We're going to do two things today. We're going to look at how the programmers program the calculator to do derivatives, and the main part of today is after we do that, you should be able to make conjectures about the relationship between a function and its derivative function. In other words, I want you to be able to answer three questions. What is happening with the original function when the derivative is negative, so what's happening on the original function when the derivative is negative, shown in a graph. What's happening on the original function when the derivative is positive, and what's happening on the original function when the derivative is 0. So those are the three main goals at the end of the notes today. But before we get to that, we're going to look at how a calculator does derivatives. So let's take a look at an example. If f of x is equal to x cubed, let's find the exact value for the derivative at 2. And this is just using the same limit definition from the last chapter. Then we're going to do it with approximates, and then we're going to make a connection here with the calculator. So, f prime of 2, that's the derivative at 2. From the last section, it's the limit as x approaches 2 of my function minus the f of c value, that's the y value at c, all over x minus c, where my c in this problem is the 2. So it's the limit as x approaches 2. F of x is our function x cubed minus f of 2. Off to the side, f of 2 is 2 cubed, that's 8, all over x minus 2. Plugging 2 in, I get 8 minus 8 over 2 minus 2, that's 0 over 0. So I know I've got an x minus 2 in here. I'll do a little synthetic division with 2 to see what the other factor is. So I've got 1x cubed, 0x squared, 0x, and negative 8. So raise the 1. Multiplying, I get 2. Adding. Multiplying, I get a 4. Adding, I get 4. Multiplying, I get 8. 0, I'm good. So, x squared plus 2x and a plus 4. Now I can cancel off. So the limit as x approaches 2 is whatever I get when I substitute into the remaining quadratic. So that's 2 squared plus 2 times 2 plus 4, 12. Okay, that's our exact derivative. We want to go back and back in chapter 1, we did our 3-point table for this, and we picked a 0.01 tolerance between our points. Let's, no, what we did back in chapter 1 was approximate the derivative. At x equals 2. And let's start all over. At the very beginning, we did a 2-point table. And what the programmers refer to that is called a forward difference quotient. So a forward difference quotient is when we went with our 2-point table. We went 2, and then we went to like 2.01. And we found the two y values. And we know at 2 it's 8. Grab my calculator here. So table, let's see, y equals, turn that off. X cubed is what we're working on. 2 and 0.01, I'm good there. So I've got 8, and then 8.120601. And we would do our difference quotient. 8.120601 minus 8.01 difference there. And we'll get subtracting, dividing 12.0601, which is very close to the 12 that we found exactly. Then what we did after that to get a better answer was we did a 3-point table where we went before and after the 2. So a 3-point table is called a symmetric difference quotient. So that's where we put the 2 in the middle. We use the 2.01, and then we use the 1.99. Let's run through that real quick, review that. So we know we've got the 8, the 8.120601. And we've got 7.880599. If you do the subtracting and the dividing here, so it's the 8 minus the 7.88, all those numbers, over 0.01. This one we already did. This one came out 12.0601 after I go 8.12 minus 8. Okay, this top one we still have to figure out. So 8 minus 7.880599 divided by 0.01. 11.9401. We average those. Divide by 2. We get an average of 12.0001. So again, very close to the 12. And then there's one more way to estimate that derivative, and that's called a backwards difference quotient. So that's where you start at your number you're trying to find the derivative at, 2, and you go backwards from that. So I'd be just using the 1.99, which we've already got up here. And we know that that came out 11.9401. Okay, so what we want to be able to do is look and see what a calculator is doing. So if you have your Texas Instruments, and they're not all the same, but I do know which way the Texas Instruments people are working. To do this on a calculator, so this is numerical derivative on a calculator. Okay, calculators are not able to do this exact stuff that we did here with this limit business. It can't do that. The best thing a calculator can do is approximate the derivative. And the whole goal of today is just to see what the calculator's, how it's programmed. Are they doing a forward difference quotient, a symmetric, or a backwards? They're going to pick one of these and go with it. Chances are it's a symmetric, but let's take a look. You are going to go under Math. You're going to look for n-deriv. That's numerical derivative. So Math, you arrow down, and so on mine it's the 8th function, n-deriv. Now, the newer operating systems, this looks completely different, so definitely take your calculator out. You still have to feed it the same 3 things. But I can't remember, I don't have a newer operating system to show you on here, so if you can't figure it out, I'll show you in class. But what you have to feed this program, you have to first give it the function that you're working with in terms of x. Then you have to tell it which letter you put in your function, and we're just going to stick with x's, so you're always going to put in x next. And then you have to tell it which number, which x value you want the derivative at. You feed it the c value. So even on the other operating systems, you still have to give it the function, the variable x, and then a number for c. So if we are to redo this problem, we wanted to estimate the derivative at 2 on the calculator. You're going to find the n-deriv. You're going to type in the equation. The equation we were working with was x cubed. The letter we used here was the letter x. And then we were finding the derivative at 2. So type that in. The equation was x cubed, comma. We used x's in our equation. And I only want the derivative at 2. $12.12345. Okay. It came out very close to our symmetric difference quotient here. The only difference is they got it a little bit closer. So the difference between what we did and what they did was probably just the tolerance level. They probably went out 0.001 or 0.0001. So they're just using a smaller tolerance than we did. We used 0.01. They probably went 0.0001 or something like that. So calculators are doing that symmetric difference quotient, at least the Texas Instruments programmers anyway. All right. So now that we know we can check numerical derivative on the calculator, now we want to be able to look at that relationship between functions and their derivative. So this is our explore. Explore the relationship between a function and the derivative function. So let's look at f of x equals x cubed minus 5x squared minus 8x plus 70.